experimental proof of a multiverse interaction. The simulation event. In early 2025, CERN scientists launched a series of quantum field simulations designed to probe vacuum instabilities at energies approaching the Planck scale. These runs, powered by a bespoke AI trained on petabytes of LHC collision data, were meant to map out subtle fluctuations in the quantum vacuum. Instead, in one particular dataset, the AI detected a metric distortion that shouldn't exist under our standard model. The simulation recorded a sudden, localized shift in boundary conditions. Virtual particles vanished and reappeared with altered quantum numbers, as if a piece of the simulation had been swapped out from another domain. This swap event lasted only 12 milliseconds, yet the statistical confidence was off the charts, over 7 sigma. Physicist Dr. Elena Moretti, who led the simulation team, describes it as a ripple in the fabric of our computed universe that doesn't compute. The AI agent, nicknamed Quanta, isolated the anomaly by comparing trillions of simulated events, highlighting a sequence of qubit states that aligned perfectly with patterns expected only if information from a different quantum sector had bled in. Could this be a simulation glitch? The team ran hardware diagnostics, no cosmic ray upsets, no memory corruption, no software bugs. Every control check passed. What remained was an event that looked like a genuine boundary breach, a signature behaving as if it came from a neighboring universe. That's not science fiction. That's CERN's data.
Here's the Lorentz attractor, a visual representation of chaos in a three-dimensional system. It looks like a butterfly or figure 8 and shows how a deterministic system can still exhibit unpredictable, never-repeating patterns due to sensitivity to initial conditions. Here's what you're seeing. Left plot, the small initial difference in just the x value, 0.0001, grows exponentially over time. This is the hallmark of chaotic systems, sensitive dependence on initial conditions. Right plot, 2 trajectories that start almost identically quickly diverge and evolve into completely different paths, even though both are following the same deterministic rules. That's chaos in action, predictable in the short run, but fundamentally unpredictable long term. Mathematical singularity theory. This theory deals with points where a mathematical object, like a function or a surface, is not well behaved. For instance, where it becomes non-differentiable or where certain quantities become infinite. Key concepts. Singularity, a point at which a mathematical object is not defined or behaves pathologically. Examples. In calculus, the function f(x) equals frac 1x has a singularity at x equals 0. In differential geometry, a cusp or a point where a surface folds over itself. Applications used in differential topology, algebraic geometry, and physics, especially general relativity and string theory. The omega point is not a conventional chaotic system like the Lorentz attractor or double pendulum. It's more of a theoretical concept than a physical or mathematical model. Let's clarify it first, then discuss how it might relate to chaos or simulation. What is the omega point? The term omega point was coined by Pierre Teilhard de Chardin, a French philosopher and Jesuit priest, who envisioned the omega point as the ultimate goal of evolution, where consciousness converges toward a final state of unity, intelligence, and complexity. Frank J. Tipler, a physicist, later adapted the concept in a scientific framework, suggesting the omega point as a hypothetical end state of the universe, where the universe contracts in a big crunch scenario. Computational capacity becomes infinite as time approaches this point. It would allow the resurrection of the dead via simulation, Tipler's more speculative idea. Omega point and chaos theory. While not a direct application of chaos theory, the omega point touches on overlapping themes. Omega point concept, relation to chaos. Increasing complexity, emergent behavior in chaotic systems. Infinite computation at the end. Sensitivity to boundary conditions and infinite evolution. Consciousness evolving, self-organization in complex systems. Deterministic universe. Chaos is deterministic but unpredictable. Simulation theory, Tipler's view. Links to computational modeling of chaotic systems. Simulation idea. While there isn't a standard omega point equation to simulate, we can approach it symbolically by simulating a chaotic system trending toward higher complexity or convergence, an evolving logistic map with increasing parameters toward bifurcation and chaos, or simulate the entropic horizon where a system moves toward infinite complexity or symmetry.